Hello. So in this section, the final part for this chapter looking at straight lines, we're going to look at modelling with straight lines. So again, we looked at modelling with quadratics earlier on in the course in an earlier chapter. So we had a real life scenario, and we needed to kind of find a quadratic equation, which will then tell us what we need to know. Okay, and we're going to use the same idea with straight lines as well. So it turns out in certain real life scenarios that we'll be looking at certain questions based on real life problems. We can use straight lines to depict the information, and then we can use that straight line to gather information that we need. And so yeah, that's essentially that's what we're going to be doing. Now, so as a recap then, what we've been doing in this chapter, well, the thing that'd be useful is, again, I'm going to probably just restate the obvious and restate the main thing we'll be doing. But a straight line, again, take a straight line here, say that one. Any straight line is in the form y is mx plus c, and that's again going to be paramount in this section. Again, seems fairly I guess like obvious, because we'll be using y as mx plus c for the whole chapter now, and in GCSE as well. But it's going to be important to just restate it again, because in particular this again is going to be the gradient, and c is the y-intercept. Okay, and so as an example here, if I then say this was the point 5 there, the y-intercept was 5, and let's say this point up here was what should I say, 1, 8. Okay, so the x is 1, a, y is 8. Then we would compute the gradient m as change in y. So that's the x-axis, and this is the y-axis. Change in y, change in x. So with any two given coordinates or points on the line, we would firstly do the change in the y coordinate. So let's take this point 1, 8, well the y coordinate's 8, and then I'm taking away by this coordinate here. Well that's the point, well that is the point 0, 5, the y-intercept is 0, 5, so the y coordinate's 5, then we do change in x, so then we take away the x coordinate here of 1, take away the other x coordinate here, but the x coordinate is 0 because it's on the y-axis, so therefore the gradient would be 3 over 1, which is 3, okay? And also then the y-intercept, intercept, there we are. Well, it's at 5, but as a coordinate, because it is a point, it would be 0, 5, okay? Therefore, we could then say the equation is y is 3x plus 5, okay? As 5 is the y-intercept, that value there. Okay, so that seems obvious, but in real life, these sort of ideas, right? The gradient and the equation, they have real life meanings. So let's then take as an example that x then is, say, time on the x-axis, but time is positive, so actually we're going to be only interested when x would be positive in that case, okay? And say y is now the population number. So what we're going to be looking at in this particular case, and I'm going to assume the same sort of line, okay? There we are. At 1, 8 and 5, okay? And this is the population number. Obviously the units may differ, but the idea is that we're measuring over time what happens to the population number of something, okay? And so now we have a real life meaning. Okay, let me write that a bit more clearly. But now we have a real life meaning for what this line is representing, right? And so we're talking about as time increases, the population number goes up. And so then, as an equation here, the population number is 3x plus 5. So if x is time, then the population number corresponds to 3x plus 5. So this working out the equation on that line allows us to compute certain information, right? That'll help us in this real life scenario. And in particular, I said at the very start, a line is defined by its gradient and its y-intercept. And then, as in real life, and in questions as well, they will have meanings as well. So gradient, first of all, which is m, here. Now that's changing y, changing x, but actually what that also means is as we increase, so as we increase x by 1, or 1 unit, so if we increase x by 1, then that tells us what y goes up by, okay? So y increases by m, okay? So remember m is the gradient, okay? So what that means is then, if we then, this coefficient 3 tells us as we increase x by 1 each time, so say we start at 0, well, y is 5. But then when we go to 1 here, well, then y becomes 8. So we've gone up by 3, okay, as x goes up by 1. And that's what the gradient would tell us. As we go along 1 unit x, right, as x goes up by 1, that means that gradient tells us how much y goes up by, okay? And so in this particular case, the gradient of this population idea is that as time goes up by 1, let's say time is in years, right? As we go up by 1 year, the population number goes up by 3. Okay, again, I'm not really given much units there. This is just a rough example. And so therefore there is a real life meaning behind the gradient, and also therefore there's also real life meaning behind the y-intercept, which again is c. Okay, as we call it. And so the y-intercept then in this case, well, what's special here is, and here, is that that's on the y-axis. That's when x is 0, okay? Well, x is 0, we call that the value of y when x is 0, okay? And so in this particular case, again, in this real life situation I'm describing of a population number and time, well, when x is 0, that is when time is 0. That's the initial time that we're starting, right? So when time is 0, that's when we're starting. So then the population number is 5 here. That's telling you 5 is the initial population, okay? So again, there is a real life idea behind that. But that's essentially these two ideas of gradients of y-intercept. You will be expected, and we will see questions in a minute, of relating the gradient, the y-intercept, to describe it in terms of a real life situation, because there is a real life meaning behind these two ideas. The fact that as we go, x goes up by 1, as again, if you see an x goes by 1 there, the y value jumps up by 3, which is the gradient, okay? And then the y-intercept is the initial value of y, okay? So that's when x is 0, okay? It might seem fairly obvious-ish, but it's important to state it because you'll see in a minute where there will be questions where we will need to explain what these two things mean. Okay, lastly then, before I jump into questions, there's a particular type of sort of straight line that you need to be familiar with. And again, we have this axis here of x and y, and in particular, it's when it goes through the origin, okay? What we call this is a direct proportion, okay? And you would have seen that GCSE, but we need to go over it now because it does come up. But a particular type of straight line, when it goes through the origin, is a direct proportion, and that is an equation where y is in the form of mx, but the y-intercept would be 0 because it's at the origin, so it's just mx, or you might see it called y is kx. Okay, and direct proportion means that the variable y we say is I want to see if I can draw this properly. Y is, and it's this weird sort of symbol here. It's this weird sort of like fish-like symbol. I'm probably not drawing it the best, but this means proportional to. Okay. and we say y is proportional to x, okay? Now, if y is proportional to x, all this means is that we can then say y is equal to kx, and this k is what we call the constant of proportionality. Which is why we can also call this line kx. Km, no matter what letter you put in front, it's the gradient, okay? But yeah, so in this particular case of direct proportion, we have this idea of a constant, right, k, which is the proportion rate, or the constant proportionality. If I can write it here, if I can squeeze it in. So as a very, very brief example, we have that y is proportional to x. So again, I'm going to use this symbol. And we're also given that when y is, I'm going to say that when x is 1, y is 4. And then we're going to say find y when x is equal to 2. Okay, very simple example, GCSE example, but I thought I'd go over it now very quickly for like an example. So then, okay, so we want to find y when x is 2, but I need to find an expression for y in terms of x. Well, that's this here. If I'm told y is proportional to x, then that means I can say that therefore that y is equal to kx, where k is that proportion constant. Okay. Well then, I'm given this information here. I can substitute it in. So then y is 4. Then x is 1, so I'm going to have k lots of 1. That allows me to find k. So that means k is 4 over 1, which is just 4. Therefore, y is equal to 4x. Okay. That means then I've got a clear expression for y in terms of x. But then when x is 2, y is equal to 8. Okay, 4 times 2 is 8. And there we are. So that's a very, very brief example, direct proportion. It can come up, and it is to do with straight lines, obviously. It's a type of straight line. And again, many situations in real life are proportional, right? So one thing is proportional to another. For example, perhaps we could say in the summer, or say in the temperature is proportional to the ice cream sales, right? The higher the temperature, the warmer it is, the more ice cream sales there would be. That's a proportion relationship there. So then basically, as x increases, oh, y increases, okay? And that's the whole idea of direct proportion. As x increases, that means y also goes up and increases as well, okay? And yeah, so I thought that's a good idea to mention it, because the textbook doesn't go over it that much, so I thought I'd dedicate a little section to it there. Anyway, so let's have a look at some examples then. Example 15. The graph shows the extension E of a spring when different masses are attached to the end of the spring. Calculate the gradient of the line. Now, the first thing to note, and probably the probably one of the difficulties of this section, is that you're not always going to be working with y and x all the time. You're going to get different letters, E and M in this case, but they're the same sort of idea. Okay, M is sort of on the x-axis, and E is on the y-axis, but instead we call it the M-axis and the E-axis in this case. Okay, and obviously in real life you're going to get different variables. Okay, you're going to use all sorts of different things, because real life is just diverse by nature. So yeah, but it's the same idea what we looked at. Just instead of y and x, we have E and M in this case. So first of all, calculate the gradient of the line. Well, that is basically the same sort of idea as we looked at this whole time. The gradient is the about between 2 points, right? The change in y, change in x. But in order to do that, I need to find 2 points on the line. Well, I know to go through the origin. Okay, so let's take the origin, which looks a bit like that. Origin is 0, 0, although it looks like another 0. I can never draw my O's distinct to 0. Anyway, I'll just say origin. Okay, and another point we could take on the line, if we read the graph, I think this point's quite nice, right? This point here, So when m is 100, e is 5. Okay. So there we are. So we've got 2 points on the line. Now we can compute the gradient, right? So the gradient is equal to changing y, changing x. So let's take 5 here. Take away the other y value of 0 because it's at the origin. Take away then the x's. So 100. Take away 0. That'd be 5 over 100, which would be simplified down to 1 over 20. Cool. But therefore that's our gradient then. Part B. Oh, and it said the gradient was k. So I'd say that k is 1 over 20. There it is. But there we are. Part B. Write an equation linking E and M. Okay, well, again, this is a straight line, and as we discussed, every straight line looks like it's in the form y is mx plus c. Where again, y on the vertical axis is e this time, so e is going to be equal mx. Okay, well, m's the gradient. We discussed this 1 over 20, right? So that's going to be then mx. Well, x is not x, it's m, because that's on the sort of x-axis. It's the horizontal. M plus c. Okay, but we don't know what plus c is just yet. Well, actually, no, we do. What's the y-intercept? Well, not the y, the e-intercept, I guess. Crosses the e-axis at 0. Okay, at the origin. So it's going to be plus 0. But that means it's just e's 1 over 20m. And in this particular case, this is a direct proportion. Okay, it doesn't ask for it, but because it goes through the origin, a specific type of line, it's a direct proportion. Okay, cool. There we are. Then part C says, what does the value of k represent in this situation? Well, k is the gradient. So here we are. It's asking what the gradient represents in this real life situation. But what's going on then? Let's look at what it's describing. E is the extension of a spring with different masses m. So if you then basically hook something onto a spring, that will pull it down, and how much the spring is pulled down is the extension, right? And that's to do with Hooke's law, but obviously that's you don't need to know that at this. But yeah. Anyway, so even if you don't know anything that's going on, we can just use the word, the sentence it gives us. So, well, the gradient is, as I discussed, as x goes up by 1, well, as m goes up by 1. So as we increase m by 1, but what's m? Let's use what it tells us. It's mass. So as we increase the mass by 1, okay? The extension of the spring, which is E, increases by our gradient, which was 1 over 20. Okay, and that's what that means. Okay, cool. So yeah, there we are. So as you can see, we basically described we basically said that as m increases by 1, that then e increases by 1 over 20 by the gradient. But I gave the real life meaning of what the question was talking about, right? Well, not m, but the mass, okay, and not e, but the extension of the spring. So I'm basically copying what's given to me in the sentence to describe exactly what, in terms of the situation, right? To contextualize it. But there we are. Cool. Example 16 then. So we're told a container was filled with water. A hole is made in the bottom of the container. The depth of water remaining was recorded at certain time intervals, and the table shows these results. First of all, it says determine whether a linear model is appropriate by drawing a graph. So a linear model meaning, is it a straight line? Is it an equation we can write down in this form? So we need to consider a straight line. Well, we don't have anything apart from these data, so it's asked us to draw a graph. Well, what graph? Well, the graph of these points. Okay. So Um, so this is going to be a graph of time against depth, okay? Um, and in general, you should look for if you're stuck about what to decide about what goes on the x-axis and the y-axis. Well, x-axis is your independent variable, so that's the variable you're changing. That's the variable you inputting, right? And then y is the dependent variable. That's the variable that changes as x changes, right? And what depends on x, right? If that makes any sense. Also called like the output. Okay, so independent variable, which is what we're inputting, which is what we're changing each time, and the dependent variables what is changing with x, right? So it depends on x, right? So in this case, well, the time has to be the independent variable. It's on the x-axis, if you will, um, because that's the time is not affected by the depth of water. However, the depth of water changes with time, so depth will be on the sort of the y-axis. If I get rid of this, uh, depth will be on the y-axis d, and the sort of I guess the x-axis will be t. Now I need to plot these data then. This data, so 0, 19.1, 10, 17.8, and so on. Well, I need to think of a scale, right? Because I need to draw my axis, but I need to draw a sensible scale. That matches all these points. Well, let's look at time first. See, time is between 0 and 120. So it's best to go from 0 to 120. Okay, that's why I got this trusty ruler here. Right, okay. So let's make it flat. But then I need to think what sort of scale I want to use. How many boxes do I want to represent each unit, right? Each number. And I think it's probably best. Well, it's going up in tens. So you could think maybe each box is 10. But I think it's best to be a little bit more like a little bit more specific than that. I'd say probably 5, because if we then draw the graph, we might then want to use the straight line to find out other missing values, which could be like when t is like 5 or something like that, or t is 2. So we need a bit more of a specific graph than just 10 units up. I'll take 5 instead. So along the t-axis, I want to start at 0. Let's say, let's say that that's 0. That, oh, God's sake, this bloody ruler. Let's say that this point here is at the origin 0. So then I'm gonna go and I'm gonna go. Each box is 5. So then 10 would be. Oh, that's not a line, right? Oh, so then 10 would be. What is going on here? So 10 would be there. Then I have 20. Oh, 20 would be there. So awkward doing this on computer. So we have 10 there. Let's do 20. Okay. That'd be. Oh, for God's sake. 20 there. Then let's go up to 40. So that'd be 32 boxes. Then 40 be there. Then let's go to 60. So that'd be 52 boxes. Another 2 boxes would give us 60. Then we go up to 80. There we are. Then we can go to 100. So that'd be two more boxes would be 90. Then 2 more would be 100. There we are. Then we go to 110. There we are. It's a bit. It's not matching. There we are. So 110 will be there. 100. 10, it's 120 with there, okay. And there we are. Okay, that's not the best graph. I'm going to draw this left bit here a bit better. There we are, okay. There we are, so it starts at 0. And each box goes up by 5, so then I get a scale of 20 for each major sort of marking, okay. There we are, okay. Obviously you can do your own scale, really, as long as it's sort of sensible and you do include all the data, then I guess it's not a big deal. But that's the scale I will rock with. Hope I've done that right. Yeah, it looks like 4 boxes each way. Okay, so then that'll be the what we call the t-axis, so t is time, so that'd be time down here. Okay, cool. Then I'm going to do the same for the depth now, which is d. So this one, it's going from, well, it's starting from 3.5, but we can say that's 0. I can start from 0 effectively. Then it's going up to 19.1. Well, it makes sense to go from 0 to 20, right? So what scale? Well, I think each box should be probably 1 then, really. I think because we've got it's quite such a broad range from 3.5 to 19.1, and we've got decimals. So I think we should make each box 1 to be sort of specific in that case. Anyway, let me draw then. Let me get a nice vertical line to draw my d-axis. There we are, cool. So we're going to go up in 1s each box this time. So starting at 0, then that's 1 there, 2, 3, 4, 5, and gone 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, cool. So that should, so that should be 20, 20. Let me get rid of this now, I don't need it. That should be 20 there, and that be your D, okay, and that be your depth. Okay, cool. You can include the units if you want to be very specific to centimeters and seconds, but yeah, as long as you've got a gist for it. So it goes up to 20, so 2 would be there. Let's go up in 2s. 4, 6, 8, 10, 12, 14, 16, 18, and 20. Okay, cool. So our axis is drawn right. Okay, I hope so. Okay, oh man, there we are. We've got that done. So now let's plot our points. Okay, so time is 0. The depth is 19.1. So 90. So it's going to be there, right? Then the next point is 10. It's 17.8. So t is 10. So it's going to be there. 17.8. So it's going to be close to 18, right? So it's going to be about there. Okay. Then 30 for time. Then 15.2. So 30 is going to be there. So 15.2 is just over 15. So it'd be about there. Then we have 60 now. We jumped up to 60, and we have 11.3. So we know 60 is 11.3. Well, 11 is there, so 11.3 would be just over it, say there. Okay. Then 100 for time, 6.1. So that's going to be just over 6, so it's going to be about there. Okay, then lastly 120 and 3.5, so that's going to be the 3's there, so 3.5 in the middle, so let's be there. Okay, cool, so we've plotted the points in. So now it says determine a linear model's appropriate by drawing a graph. So let's connect the points then, and actually it should be a straight line. And then you can see that the points form a straight line. So let's draw the line between it then. So we need to match all the points up. What are you thinking? For should we go through there? There we are. I think that might be a sort of reasonable sort of line to draw to connect through the points. Okay, so let's do it then. So a line looks like this. Okay, cool. And you know, mostly, so determine whether a linear model is appropriate. A linear model is appropriate. So can we link the time and the depth by a linear equation? So D is sort of, well, not mx plus c, but mt plus c. Okay. And that means, is it a straight line that connects the points? Well, yes, it is. It's not perfectly a straight line. For example, this point down here is a bit below the line, but all points are very, very, very close to the straight line, right? Okay, so the answer to that then for part A is a linear model appropriate? Well, yes, it is, because linear model is appropriate as the points form a straight line when plotted. Okay, so you have this nice graph here that shows it they form a straight line. There we are. Cool. Then part B is deduce an equation of the form D is AT plus B. Well, that's just what we talked about. Instead of y is mx plus c, we have D is AT plus B, but it's the same thing. D is AT plus B then. If we compare it to y is mx plus c, A is going to be a gradient, and B is our y-intercept. Okay, well then, A then a gradient. What's the gradient then? A, well, that's changing y, changing x of 2 points. So we can take any 2 points on the line. Let's take these two, okay? But we don't actually have to read off the graph because we got the points up here, right, in this nice table here. Let's take any 2 points on the table then. So firstly, this is the point 0, 19.1. So the coordinate is 0, 19.1, because remember t comes first on the t-axis. That's when t is 0, then d would be 19.1. Then the other point, let's say take this one, that's when t is 10, and d would be 17.8. So we've got 2 points then, okay? So then we can compute the gradient. So the gradient between them would be changing y, changing x. So let's take this as y, 17.8. Take out the other y value of 19.1. Then changing x, so we're going to have 10 take away 0. And so that would give me, if I put that in a calculator, minus 13 over 100. Okay, cool. So we can then sort of fill in our equation. So A is minus 13 over 100b, t, sorry, plus b. Now we need to find b then. So b is in a y-intercept. Where does it cross the y-axis? At this point here. But this point is 19.1. Is that point there? So that means b is 19.1. Okay. And we call that the d-intercept. So you used to call it the y-intercept, but because we're not on y and x and y, we're on d and t. So d is sort of the y-axis now, so it'd be the d-intercept, not the y-intercept, okay? Just a little point there. Therefore, then we got the complete equation. So d is minus 13 over 100t. You can convert it decimal if you want, but then that'd be plus 19.1, okay? Actually, I will convert decimal because I've got a fraction and a decimal. Let's put in both the decimals to be consistent. That would just be minus 0.13, I believe. 13 over 100. Yes. Okay, cool. So there we are. We've got an equation then. Then part C says interpret the meaning of the coefficients A and B. Well, again, A and B are the great. A's the great. Oh, let's go up here. As we discussed. Oh God. A up here. A is the gradient and B is the y-intercept. So that's going to help us here. So C. A represents the gradient, meaning that means as t, which is at x, as t increases by 1, but t is time in seconds. So as we increase by 1 second, so as time increases by 1 second, then the d, sort of the y value, the d value, and d's depth increases by a, so it increases by the gradient. So d again was the depth of water in the depth of water in the container. Okay, there we are. So the depth of water in the container, because that's the problem with we've got the depth of water in a container. If we read the question, what's A? Well, A is minus 13 over 100, right? That's the gradient there, right? Well, that's negative 0.13, so it decreases by 0.13 centimeters, right? Is that the units? Yes, d centimeters. Cool. There we are then. So that's A, but then we need to interpret B as well. Then I'm going to say B represents the, not the y-intercept, but the d-intercept, remember? And so what that means is, in terms of the question, the context we got. So, the d-intercept is when t is 0, so it's sort of the initial depth, right? So, the initial depth of water in a container, which is d, so d in the container is b, okay, is the y-intercept or the d-intercept, and that's 19.1 centimeters, because b is 19.1. Okay, so that's the initial depth of the water in the container. There we are. So that's what that means. Okay, cool. So I think that makes sense. As an exam tip there, it says interpret. When you see that in sort of a real life problem like this, it means you need to relate what you're interpreting or what you're defining in relation to the situation, okay? You don't just say, oh, A's the gradient, you need to be a bit more specific and say, well, the gradient, that means as t increases by 1, d increases by minus 13 over 100, which was the gradient, but more particular than that, t is time. So that means as time goes up by 1, the depth goes down by 0.13. Okay, so that's when it says interpret, you really need to relate it to the question and the problem it's telling you about. So that's an exam tip. If you do see that, you need to relate it to the real life scenario in the problem. Cool. And then part D says use a model to find the time when the container will be empty. Okay, so that's using our equation. So when the container is empty, this is talking about a container, right? I guess it looks not too dissimilar to this. Well, it has water in, it has depth of water, right? The level is the depth. Now, if there is no water at all, well, that means there's no water, so there's no depth to the water, so it's empty, okay? So that means when the container is empty, D, the depth will be 0, okay? So then we can work out T, because we have this equation here, we worked that out in part B. So then when we're going to sub D0 into our equation, which we worked out in part B, which was up here. So then D0, then that means 0 is equal to minus 0.13t plus 19.1. Okay, cool. Well, then that's just an equation to solve for t. So therefore, then 0.13t is 19.1. That means t is 19.1 divided by 0.13, which is equal to 146.92 blah 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 seconds. Okay, do we need to round it? No. So I'll just round it. I guess I'll just say 146.9 to 1 dp, I guess. And that being seconds. So when it reaches 146.9 seconds, according to this model, so this equation here, that's when the container will completely empty. Okay, cool. There we are. And so yeah, that's the whole idea of modelling, right? That's basically the whole idea of modelling. It's a really good question, this is. So you can get a model. So in real life, you have some particular values or some known points. So like here, they recorded at 5 different times the depth of the water. That allowed you to then plot it and allowed you to work out a straight line equation. Then you could use that straight line equation to then, for example, find other interesting values. So when the container would be empty, okay. And yeah, so that's the whole idea of mathematical modelling, really, is to estimate some values or a problem and convert it into maths. So like convert it to a straight line. Then you can use that straight line equation to work out other stuff. And yeah, so that's really it, really, with modelling. Let's have a look at more problems then. Let's have a look at this one. So in 1991, there were 18,500 people living in Bradley Stoke. Planners projected that the number of people living in Bradley Stoke would increase by 350 each year. Write a linear model for the population P of Bradley Stoke 2 years after 1991. Okay, so there is problems like this as well, where you have to come up with the equation yourself, kind of like what we did, but this time. Well, they still give you information, but you have to work it out using the information. So, a linear model, first of all, for the population P, T years. So, firstly, I always like to underline my units. So, P is and T years, okay? So, that means P and T are my variables, but T is independent. It's like the X variable. And P will be in terms of T. P changes with T, right? As the time changes, the population changes. So, P will be in terms of T. Now, a linear model again looks like Y is mx plus C. That's a linear model. But this time we don't have Y or X, we have T and P. So P will be in replace for Y. MX will be MT plus C. So that is my model, okay? Now I need to fill in and work out what the numbers M and C are, the gradient and the y-intercept. And that'll be what we call a complete model. If we fill in all the missing bits, all the missing constants and the missing numbers that we need. So firstly, the gradient M. So M is the gradient. Now, let's have a look at the information. In 1991, there were 18,500 people living in Bradley Stoke. Plans projected the number of people living in Bradley Stoke would increase by 350 each year. Okay. So, really, I've only given 2 bits of data. This here, or 2 bits of numbers, that bit there, and this bit here increased by 350. Now, the gradient then is, remember, it's how much it goes up by, essentially, right? As we discussed, as t goes up by 1, p goes up by the gradient, right? Well, isn't this the gradient here, 350? That's telling you each year the population goes up by 350. That's the gradient. That's the rate of change, right? sort of like the change in P over change in T. Remember the gradient was changing Y, changing X. This is sort of the change in the population as T goes up by 1. Okay, so that is your gradient there. Okay. So yeah, you do need to, you could be expected, like in this instance, you kind of have to extract the information yourself to then be able to write down the model like this. So we extracted the gradient with 350 because that tells us what it increases by. Okay. Then the y-intercept, or sort of the c value, I guess the y-intercept, but this case it's not y, it'd be p. The p-intercept, okay, well, again, they're not giving us a graph or anything, so let's have a look again. In 1991, there were 18,500 people living in Bradley Stoke. Well, that's the initial, that's sort of the initial value, right? Because remember, T is the years after 1991. If it's in 1991, that's when T is equal to 0, because that's the start of it, right? 1991 is the start that we're looking at. So that means when T is 0, that means the population is 18,500. Well, there we are then. We can substitute that in. So if we complete this, fill in this equation, P is M, which is 350T plus C. We can actually substitute this in, right, into there. So then we get P, well, P is 18,500, is equal to 350T, which was 0, plus C. Well, therefore C, well, that goes to 0, doesn't it? So therefore C is simply 18,500. And therefore we've got an equation, and that is the y-intercept. This initial, again, this initial value when t is 0, that is the sort of the p-intercept, right? And we discussed that in the last question, where b, which was the sort of the y-intercept, was the initial depth, right? So it's all to do with like the initial value when time is 0. Anyway, so we've got a c then. Therefore, p is 350t plus 18,500. There we are. So that is now the linear model to represent that. Part B. Okay. Okay. Part B then. Write down one reason why this might not be a realistic model. Right. Okay. So that's basically asking to be critical, right? Well, think about what this model's saying. It's a linear, it's a line, right? So if we look like that, that's telling you the population goes up by the same amount every year. Well, with that in mind, is that realistic? Is it realistic for a population to go up the same amount every year? Population is very volatile. Loads of things can happen to change the population drastically, up or down every year. Right, so no, it's not realistic, not the exact amount. So it's not realistic, a model. As population, yes, so as the population would not increase by exactly the same amount each year, right? Gonna scroll down. Each year, okay, and that exact amount is the gradient, remember, as well. So we could say that's 350. No, it wasn't. No, it wasn't. Yeah, 350. So, yeah. So again, there are also flaws with certain models that you need to scrutinise as well. But we'll look at more examples as we go on. But yeah, so there we are. So yeah, so we're going to look at some examples now. That can be quite a fairly tricky question, looking at it for the first time. But we're going to look at more questions like that now. So we're going to look at exam questions because I think the textbook, whilst it's good practice for this particular topic, the questions are a little bit different. So I thought it'd be best to practice exam questions. But the textbook questions aren't bad. Similar to what we just did. But let's have a look at this then. So exam question, So it says the distance a particular car can travel in a journey, starting with a full tank of fuel, was investigated. Okay, from a full tank of fuel, 40 litres remained in the car's fuel tank after the car had travelled 80 kilometres, and from a full tank of fuel, 25 litres remained after the car travelled 200 kilometres. Then it says using a linear model with V litres being the volume of fuel and D kilometres being the distance the car travelled, find an equation linking V and D. Okay, typical, a lot of words there, but let's just highlight the main stuff. So, this is in bold, okay, linear model, again, that's going to mean it's going to be in the form where it's mx plus c, that's a linear equation, right? Okay, but then what are our variables? Well, it's not y and x, we have v litres, oh, and d kilometres, so we've got v for, I don't know what V stands for. Volume of fuel. There we are. V for volume and D for the distance. Okay, so those are variables. Okay, well, okay, which way around is it going to be? Well, V actually depends on the distance D, isn't it? And it kind of gives you a hint here as well, the way they phrase the question. It wants V in terms of D. It wants V in terms of D. So that means V is going to be where Y is. And so if it's with D, that means it's going to be MD plus C. But again, M's our gradient and C's sort of a V-intercept, not the Y-intercept, the V-intercept. And yeah, but also because, well, the volume of fuel is going down after the car travels so far. So that means the volume of fuel is dependent on how much the car's travelled. So yeah, that'll be Y as well. But there we are. So we've got this equation then. So we've got this equation linking V with D. However, you need to fill in the missing numbers, right, that we need to fill in. That's M and C. Because we only want V and D on its own. We don't want M and C unknown as well. The only unknowns is V and D. So, we need to work out M and C then. So M again is the gradient and C is the y-intercept. However, I do think with these type of questions, I think it's better to just substitute values in rather than just try and find a gradient or y-intercept or whatever. I think it's a lot easier and probably a bit more intuitive to do it that way. What I mean by that then is these two sentences represent two different points, two different values, right? So what I mean by that is, well, it says 40 litres remained in the car's fuel tank. Well, that means that 40 litres V's 40, right? And the car had travelled 80 kilometres. Well, that's D, that's distance, so D would be 80. So therefore we've got a first set of values, V's 40, D is 80. Now that I can substitute into this equation here, okay? So then when V's 40, I get MD, that's 80M, because D would be 80, plus C. Okay, that's fine, that's one equation, but we've got another bit of information here, so we can get two equations. Actually, I'll leave it there, V's 40, I won't rub that out. And then what about this one then? In this sentence then, this second bullet point, from a full tank of fuel, 25 litres remained. So that's when V is going to equal 25, right? That's the volume of fuel left. After the car travelled 200, well, again, that means D is 200 kilometres. So there we are. And again, underline your units here. That's why I underline it. Because V litres, that allows me, if I underline the units I'm working with, that allows me to quickly extract the values I need from the question. And so therefore, when V is 25, D is 200. But therefore, I can get another equation by substituting those values into this equation. To then get V is 25 equals 200M plus C, okay? Well, these are simultaneous equations, aren't they, right? And I know how to solve those. I've looked at that before. So, let's solve them simultaneously. So, let me rewrite let me bring this equation forward again. So, then I get 40 is equal to 80M plus C. which is equation 1 and equation 2, okay? Well, I could solve them simultaneously, so I could substitute or eliminate, but I think I can just take them away, because if I take both equations away, plus c and a plus c, the c's will cancel. So if I do say 1 take away 2, well, 25 take away 40 is minus 15. Then 200m take away 80m is 120m. Then c take away c is 0. So that's what I'm left with. Well, that I can just divide by 120 to get m, because then m is minus 15 over to 120 to then get an eighth. Okay, that goes to an eighth and minus an eighth. Cool. Okay, well now I've got m, I can substitute it back into either of these equations here. Let's do the first one. So I'm going to sub m into the first equation. Then I'm going to get 25 is equal to 200m, which is minus an eighth, plus c. Therefore, 25 is equal to 200 times an eighth. I get minus 25 plus c. Therefore, if I add 25 to both sides, I get that c is 50. Okay. Therefore, my equation now is v is md. That m is minus an eighth d. Plus c is the plus 50. There we are. Cool. Now that's an equation we've got there. Cool. Then it says find according to the model there. Find according to the it says given that on a particular journey the fuel tank of the car was initially full, the car continued until it ran out of fuel. Okay. Find according to the model the initial volume of fuel. Well, that was in the car, that was in the fuel tank of the car. So the initial volume is when, well, it's at the start. If it's at the start, the car's not moved any distance, so that means when d is 0, okay? And so I'm going to restate my equation I worked out. V up here, so v is minus an 8d plus 50. Well, d is 0 is the initial volume when the car hasn't moved. So it's the full tank, right there. So it says full tank initially. So in d0, let's substitute it into here. V is minus an eighth of 0 for d plus 50. But that means v is 50. Okay. And that being litres, remember again. Remember we underlined the units. They're v and d, litres and kilometres. And there we are. So that would be the initial volume. So that's the full that's the full volume of the car, right, of the fuel. There we are. Then the second part says the distance of the car. Find the distance of the car travelled on the journey. Well, obviously when the car runs out of fuel, it stops moving. Well, there it is. So then, therefore, it starts from a full tank, and then at the end, it ends up with nothing in the tank. So that means v0 corresponds to the distance it travelled, right? So let's substitute v0 into it. So that means 0 is minus an eighth d plus 50 by substituting 0 into the equation. Therefore, an eighth d, if I rearrange, is 50. So that means d is 50 times 8. To then get 50 is 400 kilometres. There we are. Cool. There we are. Great. And there we are again. See, like the modelling. See, you can work out other info. You can use the model, convert it into an equation, to then solve that equation to find other other information like this. So the initial volume and the distance the car travelled. So there, it's very, very useful in modelling situations in this way, converting it into a mathematical equation, and then work out other stuff. Anyway, then for this last part, it says, in fact, the car travelled 320 kilometres on this journey. Evaluate the model in light of this information. Well, it told you that in reality, the car has only travelled 320. Well, 320, 400 in this case is quite different, right? Um, so 320 kilometers is, well, it's quite different, significantly uh, different to 400 kilometers, right? And to put that in context, that 320 divided by 400, that's 80%. So actually, the model is off by 20%. Now that's actually fairly rubbish. Okay, usually you allow for like probably up to maybe like 5% error, perhaps, in a model. If it's above that, it's like 20%. It's quite rubbish. It's a bad approximation. Okay. So in that respect, it's significantly different to 400 kilometers. So it is an unreliable model. Okay, and there we are. Cool. If instead it was like the distance was like 397, then yes, whilst it's different, yes, it's not that far off. But 320, like I said, is 20% off. That's quite major, really. When you're trying to use it to work out accurate information. Um, so yeah, there we are. There we are, cool. So yeah, that's quite typical as well, where you need to model to work out predicted information. So in this case, the predicted distance a car travelled. Because bear in mind, this is all predictions, right? I've only got given 2 points, and therefore I'm creating a whole equation based on those 2 points, which I'm using to predict every other possible point. So that's a lot of like that's a hefty approximation, that is. So these models are only approximations. They're not going to predict every value in its entirety, but we do still need to make sure that the information the equation gives us is fairly close to the real life thing, which is the whole idea why we use it, right? To model. Okay, we've got a final question now, and this is a tricky question actually. We'll see in a minute. Okay, but let's have a read of this one then. So a small factory makes bars of soap on any day. The total cost of the factory, Y pounds, of making X bars of soap is modelled by it to be the sum of two separate elements, the fixed cost and the cost that's proportional to the number of bars of soap that are made that day. Write down the general equation linking Y with X. Okay. Now again, probably because we're in this chapter, you're probably going to realise it's a linear equation, right? We're doing linear stuff. However, I don't think it's immediately obvious we're working with a straight line model, a model that looks like y is mx plus c. Well, spoiler alert, that is the answer to part A. Okay, this is a general equation. It says general, meaning you can include missing constants and values. But when if it said write a complete equation, then that means we need to fill in any missing values. We need to find the missing values m and c. But because it's a general equation, we just need to give the general equation what it looks like, right? So there we are. That's part A. However, yeah. So obviously m then is the gradient and c is the y-intercept again. Well. So we are told there's a fixed cost and the cost that's proportional to the number of bars of soap. But let's have a look at that. The cost then, we know what proportional means. It means that proportional to the numbers of soap, well, the numbers of soap is x. So that means it has to equal kx, right? This proportional cost. Okay, think back to the direct proportion stuff I talked about at the start. So that's the proportional cost. Then there's also a fixed cost. Okay, and that's a cost I'm going to add on no matter what. So I'm going to call that just add c, right? Well, and then that's equal. Then that's the total cost. These two together, again, it's said the sum of these two parts. That's equal to the total cost, which is y. Well, hang on a minute. If I just call k's m here, But therefore I get the equation mx plus c. Okay, so this is actually turns out to be a linear model. Okay, although it can be fairly tricky to realise that, but yeah. Uh, but yeah, okay. So again, fixed cost will be plus c, and proportional cost will be kx. Okay, if you add those together, I get kx plus c, which is in the form of mx plus c. There we are. Okay, but there we are. But I'm going to call it m instead. But there we are. That's our equation to part A. Cool. Then part B then says the bars of soap are sold for £2 each. On a day when 800 bars of soap are made and sold, the factory made a profit of £500. On a day when 300 bars of soap are made and sold, the factory made a loss of 80. Using the above information, show that y is this. So actually it's showing you that you need to work out the values m and c in this case, because they're giving you some information. Okay, so this is what makes it challenging, because it's a bit different to the other problems. And so I'm going to explain this now. I'm going to get rid of this part B for a second. The deal of throwing this in, they don't explicitly teach you it in the book. I guess it's sort of common sense, but you need to be aware of the idea of profit, cost here, and sales, so how much you sell stuff for. And that's a business thing, and in general what we have is the profit you make in a sort of business activity. The profit is the total sales, right, that you have. So that's how much you sell a product for. Think about a shop, right? The only way you can make money is if you sell it to a customer. So you get sales minus the cost to produce that thing, right? So in this case, the cost to make the soap. The remaining money you get left after you sold it, and then you cover the cost, everything you needed to make it. The remaining thing you get left is your profit, okay? And ideally, profit, you want it to obviously be as big as possible to make it a lucrative company. But again, it might seem like to some people, fairly obvious equation, but you do need to remember it actually, because it doesn't, it's not explicitly taught in the textbook. I guess they assume you need to know it, but you do need to remember, even if it is obvious, in a minute you'll see it's really handy to actually write this equation down, because it allows you to more easily work with it. But we'll see that in a minute. But yeah. So in general, when we're dealing with selling stuff and it talks about profit and cost, you might need to use this formula. Profit is sales minus cost. So again, in this case, the bars of soap are sold for £2 each. So each bar of soap, the sales is £2. And then the cost of each bar of soap, I don't know what that is, but if you take that away, then you get the profit of selling a soap. Okay. And ideally, and also profit can be negative if it costs more than it does to sell it. And you can see that here. If it makes a loss of 80, that's a negative 80 profit, okay. And also you can rearrange it if you need sales or cost instead. But yeah, that is the key formula there, and I thought I'd dedicate a little bit dedicate a segment to it here. Okay, so let's commence with part B. So we are given, again, two bits of information, two sentences. So, on the day where 800 bars of soap are made, the factory makes a profit of 500. On a day when 300 bars of soap are made, the factory makes a loss of 80. Okay. So, again, we need to kind of extract information from that. We need to get a value for y and x, okay, from this. So, firstly, well, 800 bars of soap, that's when x is 800, right? Then it says the factory makes a profit of 500. Okay, but let's remind ourselves, what is y? Well, x, remember, is, y is the total cost to the factory on a day, right? And where's x? Oh, x bars of soap. Okay, so x is the number of bars of soap, and y is the total cost. Okay, but we have profit here. Profit is not cost. Okay, so that's the profit. Well, in order to work out cost, we need the sales as well. Okay, Well, the sales, they're not told it in this sentence, but it's up here. It says the bars of soap are sold for £2 each. So if one bar soap, I'll make the note here, one bar soap equals £2 sales, right? That means we have 800 bars of soap here, X is 800. That means the sales is 800 times 2. So the sales is going to be 800 times 2, which is £1,600, okay? Therefore, the cost then is going, if you rearrange this highlighted equation here, cost is sales minus profit. So it's 1,600, take away 500. That's going to get me 1,100. And that's going to equal y, because y is the total cost, okay? So there we are. So we had to do a bit of work there to get the the values that we want. But now we've got x and y, I can substitute it into this equation I found in part A. So that means y is 1,100 and mx is going to be 800m plus c. Okay, that's one equation. But I've also then can use this second, what's it called? This second sentence here. On a day where 300 bars of soap are made, well, that's going to be when x is 300. That's the number of bars of soap. The factory makes a loss of 80, so that means the profit is negative 80 here. Okay, well, that's profit. Well, then I need the sales, okay? In order to work out the cost, I need both of these. Again, the sales, again, each bar soap is £2 sales each. So it's £2 each, then there's 300 bars, so it's 300 lots of 2, okay? That's my total sales of 600. Therefore, the cost then is sales take away profit. So 600 take away minus 80, that'd be add 80, so it'd be 680 there, okay? And that'd be your y, okay, because y is your total cost there. But therefore, we've got another bunch of values to substitute into the equation. So y is mx plus c. That means 680 is 300m plus c. Okay, well now I've got two equations again, here and here. Let me rewrite the top equation down here again. So 1,100 equals 800m plus c. If I call that equation 1 and equation 2, then I can solve these simultaneous equations for m and c. Well, I can take them away to get rid of c, can't I? So then if I do 1 take away 2, well, 680 take away 1,100 gets me minus 420 is equal to 300 take away 800m is minus 500m, and c take away c is 0. So then therefore m is minus 420 divided by minus 500, and that will get me 21, positive 21 over 25. Cool. Okay, and as a decimal, so that would be 0.84. Okay, well then I can find the c value. I can substitute m into either equation here. So that means I'm going to say sub m into the top equation, so into the first one. Then 680 is going to equal 300m of 0.84 plus c. Therefore 680 is 300 times 0.84 is 252 plus c. Therefore c is 680 take away 252, and that'd be 428. Cool. Therefore, our equation then is y is mx plus c. It's 0.84x plus 428. Okay. And there we are. There we are. We've got the equation I wanted. There we are. We got that. Then it says for part C, I'll do part C here then. With reference to the model, interpret the significance of the value. Again, interpret, key command word. It means describe it in terms of the real life context of the problem. Interpret the significance of the value 0.84, where 0.84 is your gradient. So remember that describes that as x increases by 1, y increases by 0.84. And so interpreting that, putting it in real life, well, x is 1, that's the number of bars of soap. So as well, as x increases by 1, meaning as we make an extra bar of soap. So as we make an extra bar of soap, I need to scroll down a bit. As we make an extra bar of soap, so that means when x goes up by 1, y goes up by 0.84. So y is the total cost of the to the factory. So the factory increases by 0.84 pounds or 84p, depending how you want to write it. But there we are. Cool. So yeah, don't lose easy marks like that, and make sure you understand it's a similar sort of idea every time, right? When it says interpret a particular value, do try to understand what we're doing here, because they are easy marks once you learn how to write your answer. But yeah, cool. Part D then, it says then, assuming that each bar of soap is sold on the day it's made, find the least number of bars of soap that must be made on any given day for a factory to make a profit. Okay, so it's talking about for the factory to make a profit that day, so it's alluding to that idea of profit, sales, cost idea again. So to make a profit that day, remember we can have negative profit. So you go from negative profit, and then you go to zero profit, then you go to positive profit. And sometimes we call that zero a break even. You might hear that, where a company just about turns from negative to positive profit. And that's what it's describing. It wants the day for the factory to make a profit, that's when it starts to make zero profit, or it goes up from there. So the point where it starts to make a profit is when the profit is zero. Okay, and again we can call that the break-even point if you want to be fancy. But the profit then needs to be zero when it starts to turn a profit or make a profit. Okay. So the profit is zero, but then if we then relate to our formula, we need sales minus cost. Okay, so that means if profit is zero, that means that therefore zero is sales minus cost. So that means sales is equal to cost. Okay, but okay, how do I work out one or the other then? So cost is y. Okay, so that means y is equal to sales. But then what's sales? Well, sales is the same thing that we saw up here. Each bar of soap is sold for £2 each. So if there are X number of soaps, because remember X is the number of soaps made, well, the sales, if each bar of soap is £2, if there are X bars, that means there are 2X pounds, right? 2 times X. So therefore the sales is Y is 2X, okay? So profit is 0, sales is 2X, okay? And therefore the cost, which is Y, cost is Y. Remember the total cost. We get this equation here. Y, which is the cost, is equal to sales, which is 2x, when the profit is 0. Well, Y, we worked it out in part B, this equation here. Y is 0.84x plus 428. I could substitute that in, right? So 0.48x plus 84, sorry. 84x plus 428, and that's equal to 2x. Well, this is an equation to solve for for x here now. So if I move all the x's to one side, so 428 is 2x, take away 0.84x. That will give me 1.16x. Okay. Therefore, x then is 428 divided by 1.16, and that would get me 368. Let me do that down here. 368.965 ... bars of soap. However, so what's it said? What's the question saying? Find the least number of bars of soap. Well, that's it then. That's the number of bars of soap where it makes zero profit. So that'd be the least number of bars of soap needed to make a profit, okay? But the only issue is, this is a nasty decimal. You can only have a whole number amount of bars of soap, right? So we're going to need to round it up. So that's going to be 369 to near, well, rounded up to nearest integer. Or whole number, okay, depending on you write it. Okay, so that's 369 bars of soap, which should be X, okay, cool. So there's our answer then. There we are, and that's really it then, that's the question done. Okay, yeah, so yeah, this question is, I think it's a lot more complicated with the fact that we have this added complexity of this profit idea, but hopefully you can start to make sense of it now. And once you understand the idea of profit, sales, costs, and how we use it to solve a problem like this, you can tackle similar sort of problems as we look further ahead in the course. Uh, but yeah, it's just something to be aware of, this profit idea. They do expect you to know it, and hopefully that made some sort of sense there with the profit. But again, hopefully the main idea is you understand how we can model and how we can write stuff into linear equations, again, in White's mx plus c form, and how then we need to extract information to then substitute into our model. So, for example, we can use these two sentences when x is 800, the cost towards here 1100, and then we could substitute that into this equation to then to find the missing values m and c to complete our model. But yeah, so it's the same sort of idea, right, of finding missing points or finding values to substitute into your equation to work some out, okay? And also don't forget this idea of interpreting the meaning of a gradient and a y-intercept, okay? I went over that at the start, remember? But yeah, don't lose easy marks with that by just writing a sentence about it. But yeah, so that's modelling then, and that's the end of straight lines. But I'll see you next time.